Hello everybody. What I'm going to do in this video is tell you how to solve pretty much any relative velocity vector addition problem. And then I'm going to show you how to do problem 73 from chapter 4 of the textbook. Okay, so when you've got two objects that are moving relative to something else, like for example, this example, we've got two ships that are on the ocean, and we're given the velocity of the ships relative to the ocean. And then we want to find the velocity of the ships relative to each other. Okay, and so I'll just explain in context of the problem. Right, so we're told that ship A is moving at 24 knots and in a direction 45 degrees west of north. Okay, so we, again, make a diagram, clearly label it, put in all the information that you need. Don't be afraid to take up a lot of space. The better your diagrams, the better chance you have of solving the problem correctly and seeing details that you might otherwise miss. Okay, so now this is the velocity of A relative to the water. Okay, now we don't know how the water is moving, but that's okay. We're not concerned about that because ship B is also on the water. Okay, and ship B is moving at 28 knots, 40 degrees west of south. Okay, so I draw that out as well. Now, what the problem asks me to find is the magnitude and direction of velocity of ship A relative to B. So I want to find the velocity of A relative to B. So here's how I write this out. I write V sub AB. That means I want to find the velocity of A relative to B. Okay. Now, what I have are the velocities of both ships relative to the water. That's the third thing here. Now, if you write it like this, see how I've got this? The velocity of A relative to the water plus the velocity of the water relative to B. Notice that the W is in the middle. It's like if you look at just the subscripts in that right half of the equation, it's AW, WB. So when you put those together, the W's sort of disappear and you get the velocity of A relative to B. So that means if I want to find the velocity of A relative to B, all I have to do is arrange the arithmetic like this: the velocity of A relative to the water plus the velocity of the water relative to B. You add it up and that's it. The nice thing about the notation that we have, the unit vector notation, is it makes it really, really easy to do this. Like with most of the vector problems, two-dimensional problems, we're going to break up the vector into two components, into the vertical and the horizontal, right? In this case, the I and the J, we would call it. And then we're just adding together. But here's the trick. Here's the place where you might get a little bit mixed up. We do not have, in the problem, we're not given the velocity of the water relative to B, right? This vector down here, this is the velocity of B relative to the water. Okay. Well, if you have the velocity of B relative to the water, what's the velocity of the water relative to B? It's just the negative, right? And so when we're writing out this equation, right, the velocity of the water relative to B, that's equal to the negative of the velocity of B relative to the water. So this equation then becomes, this is what I'm going to use to solve this, the velocity of A relative to B is the velocity of A relative to the water. I'm going to put plus negative the velocity of B relative to the water, because that's equivalent to the velocity of the water relative to B. Now that I have the velocity of B relative to the water, I'm just going to take the negative of that. How does that work? Well, in the unit vector notation, it's just the negative of each component. So the first thing, of course, is then to find the components here. So I'm going to find this. I'm going to find this using trigonometry, etc. So this is going to be, what, 24 cosine 45, and then this is going to be 24 sine 45, or 24 root 2 over 2, however you want to do this. If you want to use what you remember from the unit circle, that's great, but you can't do that for 40 degrees. this turns out to be, zoom in a little bit here, 16.9 J, and it's the same for the other. Okay, because it's 45 degrees, so it's the same for both. Here, again, this is going to be 28 cosine 40, which turns out to be 21.4 J. And then this is going to be 28 sine 40, which is going to be 18 I. And I'm keeping in mind that this is, negative. This is negative 18 I. So when I'm putting this in now, so I'm continuing my work here, the velocity of A relative to the water is negative 16.9 I, right? Because that's this vector right here, right? And it's moving in the negative x direction. So now plus 16.9 J, that's the vertical. Now plus I have it's going to be negative, and then plus the minus, right? So negative, and then this component, I forgot to put it down here, but this is negative 21.4 J. So minus negative 21.4 J, and then minus, again, negative 18 I. And that's a little bit confusing. But remember, we're just reversing everything. When we add all this together, we end up with 1.1 I plus 38.3 J. All right, now let's see, does this make sense? With the way that these boats are moving, they're both moving to the left, so it would make sense that their relative velocity horizontally would be pretty small. So, okay, we're good with that. And then this is, oh yeah, A relative to B. And so B, we notice that B's horizontal velocity is a little bit faster, so it makes sense that relative to B, A is moving to the right a little bit. And then relative to B, we would expect A to be moving up, like north, right, in the J direction pretty fast, because they're moving in opposite directions that way. And that's what we find, 38.3 J. And this is in, what are the units here? I think it's just knots, right, which I'm abbreviating as KN. Now, they want me to find the magnitude and direction. So we recombine everything using trigonometry. I'm not going to go through the details of that. I think you know how to do that. 38.3 is what it turns out to be as the magnitude, knots, at an angle of 88 degrees north of east. Okay, so that's the answers to A and B. And then C is asking, after what time will the ships be 160 nautical miles apart? This is really simple, right? If you have the velocity and you're looking for the distance, you're just going to take the distance and divide it by the velocity. So for C, you take 160 nautical miles. I'm not sure the official abbreviation for that. I'm just going to do NMI over 383, because a knot is a nautical mile per hour. Nautical mile per hour. Notice that when you deal with the units, nautical miles divided by nautical miles per hour, you end up with just hours. And that turns into 4.18 hours. And then they want to know the direction of B relative to A. Well, it's just the reverse, right? So 88 degrees north of east, if we have that would be this direction, right? Pretty close to 90. North of east, here's 88 degrees. And so the opposite, the direction of B relative to A, would be like this. And this is 88 degrees, we could say south of west, or 2 degrees west of south, however you want to put that. The real key, though, to this and a bunch of the other types of problems is the what I call the vector arithmetic. It works. And if you're really careful and just go step by step and you have good diagrams, the vector arithmetic works. It simplifies the whole thing. And the whole idea is to go back and forth in your mind between the diagram, a good sketch, the vector arithmetic, and you're checking as you go, because it's easy to get lost with all the negative signs, especially when you're switching around certain vectors. Okay, but this vector arithmetic is the real key to solving this kind of problem. And that's kind of the amazing thing about physics in general, right? Is that we can rely on some mathematical tools, rely on them very heavily, and yet they are reliable for giving us information about the physical world. It's pretty amazing. Even, as you get more and more advanced, you have to rely on things in that kind of way, and yet they continue to give us accurate results. So thanks for watching. Don't forget to like and subscribe.